The one that we're proposing with in semiconductors is the only one that I'm aware of that is concrete, experimentally verifiable, and can be done at room temperature, and would have a very clean-cut result. The rest of them are more exotic. Okay, to introduce this particular Maxwell demon, take a piece of common aluminum foil and bite on it with a metal filling, and it's usually found to be pretty unpleasant. What happens is that you have electrons which can be transferred between the different metals, between the aluminum and the silver mercury amalgam in the filling. And as the electrons are transferred between the two metals and kind of even out between them, this charge transfer amounts to a current which can be felt through the nerves and beneath the filling and gives you a slight and unpleasant shock. This demonstrates that when you bring two metals together, you get what's called a contact potential, which is the potential difference between two different pieces of metal, two different kinds of metals, as the Fermi levels, as they're called, even out between the two metals, as the water levels of the electrons, so to speak, find a common level. That causes one metal to charge positively, one to charge negatively, and that establishes a potential difference between the metal, a voltage, usually on the order of about a volt or so. Well, the same kind of thing can happen if you have two different kinds of semiconductor. Semiconductors, of course, are ubiquitous in society. They're things largely made out of silicon. They're small, very small devices, and they're doped. That means contaminated with very small impurities, 1 part in a million or so of impurity elements. There are two basic kinds of impurities: ones which render up electrons into the silicon lattice, and ones which create positive holes in the silicon lattice. The ones that liberate extra electrons into the lattice are called N-type semiconductors, and these would be created by doping, let's say, 1 part in a million or so into the silicon of something like phosphorus. On the other hand, if you were to dope it with a different element, something like boron, that would create excess holes in the lattice, and you can create two different kinds of silicon, one which is N-type and one is P-type. And if you were to join them along an interface, the ones with extra free electrons, these extra electrons can diffuse into the positive, or the P-type silicon, and the holes from the P side can diffuse into the N side. This cross-charge diffusion creates a charge imbalance across a very small region called the depletion region, where you have positive charges here, negative charges here, and this creates an electric field in the silicon and a potential difference between these two pieces of silicon, which is on the order of about a half to a full volt.
Is this a common occurrence, or is this something with specially doped silicon that you have?
Not at all. This is found in your electronic watches, your computers, anything that has a transistor in it. This is what's called a PN diode, or an NP diode. These are very, very common electrical devices. They're the mainstay of semiconductor electronics. This process is well known, understood theoretically, and verified experimentally. There's really no question that this occurs, at least within the scientific community presently. Now, if you were to take this particular piece of silicon and kind of bend it around into a new shape, like this, you would still have the charge diffusion right at this junction here, and you'd have a different potential on this side versus this side. This side would be biased positively, this side negatively, by this charge diffusion. If you then wrap this around and bring it down to to a region where you have a physical separation opening between these two, if you have positive charges here, negative charges here, that establishes an electric field across this region, and there will be a potential drop across this region equivalent to the one here. What this electric field does, well, I shouldn't say does, the electric field stores energy. And the electric field energy I can write down, it's proportional to the square of the electric field intensity, or strength. The stored electric field energy here turns this device essentially into a capacitor. This is a capacitor which stores electrostatic energy in the gap. You haven't paid for this. You have not hooked this up to a battery. You have not. There's no external voltage source associated with this. This has established this energy in this yellow region, the electric field, solely by the existence of this depletion region, which is unavoidable. So you now have a capacitor which in principle will stay charged forever. Now, capacitors, they're used in electronics to drive all sorts of things like the flash cameras, which Tony has, or cardiac defibrillators you find in an emergency room or something like that. And what a capacitor does is that it stores electric field energy. Well, if this stores energy, it occurred to us whether we could extract that energy somehow. And one way which we found we could do it, there are several ways, and I'll go over both of them, is to use just a small plug of a dielectric, just as a piece of metal is pulled into a magnetic field. Dielectrics are pulled into electric fields. So you can imagine that if you were to put a small plug of material here that moves frictionlessly within this channel, it can get pulled into the electric field. And if this were also a conductor, it could conduct the positive charges and negative charges together and have them short out, which would kill the electric field, leaving a larger electric field ahead of them, which would continue to pull this plug forward in the field. As it shorted out the field here, it would still see a higher field here, being pulled in this direction. The field back behind it would not have recovered as fast yet. The field ahead would always be larger, and this plug can be pulled all the way through the channel. As it comes to the end of the channel, there's no further electric field here, so it's no longer being accelerated. But meanwhile, the electric field behind it has been rebuilding itself. Once it rebuilds itself, it pulls the plug back, and the process can repeat again and again. We have shown, based on calculations of real dielectrics with real frictional coefficients, with real electrical conductivities, that in principle you could build a small plug, something on the order of a fraction of a micron in size, which could be pulled in and out through this channel millions of times per second and never really stop. It doesn't require, you require no power source, because the power is being supplied by the electric field, which itself is being generated by thermal processes somewhere else. So this would be a non-sentient Maxwell demon. It challenges the second law by creating organized motion out of thermal processes, out of heat. There is no other power source driving this. So that's one version of a Maxwell demon. If you were to tie a small magnet to it and have it go in and out of a coil of wire, you would have an electrical generator. So you could, in principle, generate electrical power from this mechanical motion, in principle. Well, I came up with the idea probably about 4 years ago, 3 or 4 years ago, something like that. It took about a year to develop it. Dr. Jeffrey Wright was instrumental in helping carry out numerical simulations, as was Andrew Putnam, one of my former students. They've done a terrific job.
Do you have constraints with regard to the weight of the piston, the mass involved, the drag, and all those kinds of things?
Yes, we've investigated what we consider all the salient parameters of the system, including electrical conductivity, dielectric constants, mass, friction, all of these, and we find that if you build it small enough, something smaller than about a micron in size, you can make a device which in theory should be able to perform as indicated in this video.
Have you built that yet?
No, we have not. We would like to. The technical difficulties put it probably at the state of the art of micro manufacturing, maybe a little bit beyond, but we think within the next 5 or 10 years the state of the art for micro electromechanical and nano electromechanical manufacturing will probably reach the point where this could be manufactured if there was the will to do so.
And okay, does this put out more than it takes in? I mean,
well, I mean, again, this is a theoretical study we've done. This is not an experimental study. Based on the theoretical studies, yes, it should be able to put out more. It should be able to take energy, heat from the heat bath, and turn it into mechanical work at a power rate and a power density which is rather large, in the sense that if you calculate the volume of this device, each one of these devices will put out roughly a nanowatt of power, which is a very, very small amount. But these devices are very small themselves, about the size of a blood cell. So if you were to stack them all together into something the size of this table, they could instantaneously put out as much power, in principle, as a nuclear power plant. Yes, way. You work out
the problem would be that you would freeze the entire room.
Well, it would freeze. Well, no. See, the problem is that if it's turning heat into work, I mean, it would put out a power level of about a gigawatt per cubic meter. But this thing would cool down to roughly absolute zero in 3 seconds if you run the numbers.
So you're not creating energy from nothing. What you're doing is you're converting thermal energy into mechanical energy, and that thermal energy has got to come from somewhere.
That's right. The room is full of mechanical energy. Let me give you a demonstration. If you take this table here, this table is at roughly about 300 Kelvin. Okay, about room temperature, 20 degrees C. The molecules in here are all moving about in this table at roughly the speed of sound, but they're all moving in different and random directions such that all their momenta essentially cancel. If you were to divide up this table perfectly into those molecules which are moving to the left, to the right, forward, backwards, up and down, and simply divide those up, this table would decompose at the speed of sound. All 6 parts going in opposite directions at roughly the speed of sound. That's how much energy is intrinsically present in this table in the form of heat. And that's true of everything else. Your shoes, your legs, you, all the other tables, the wall, the ceiling, the air, all of these have intrinsic energy, but you can't tap them because of the randomization of the molecular motions. They tend to cancel each other out, and it's very, very difficult to rectify them. In fact, to rectify their motions creates more entropy than the reduction in entropy that this rectification would imply. That is what the second law says. You can't achieve this rectification without paying for it, and paying for it dearly. So in subverting the second law, what it in principle would allow you to do is rectify the intrinsic heat in a room like this, and as a result, you can run all the appliances in the room forever without ever plugging anything into the wall, simply recycling the heat energy again and again. And that would be a rather wonderful thing. It could in principle be a solution basically forever to an energy problem. As long as the universe is not frozen, it will have plenty of energy to run itself. It's all present here.
And you could, in theory, have some other thing that generates heat next to it to balance out the...
No, not really. I mean, think about it. If you run the TV camera you're using right now has a battery in it.
Right.
That battery is running it, but most of that energy ends up as heat, which goes into the room.
Right.
If you had something which could collect that heat and reuse it, it would simply take that heat, turn it back into electrical energy, and run your camera again. So it's not like you've ever lost the energy. It's just being turned into another form, which you could recycle. When we developed this, we recognized that this is the electrostatic equivalent of a magnetic railgun.
Right, exactly.
But it's not magnetism. It's electrostatics here.
Right.
But this is an electrostatic railgun in a sense. No one's ever come up with this, and it only works at a small scale. This will not work on a tabletop size. It will only work when you have very intense fields on very small objects, and for it to be sustained by the intrinsic biasing of this semiconductor requires that it be submicron or in size.
Because of the nature of semiconductors?
Well, because the forces are so small, you only can move small bits of matter, and so you have to build them very small. And to get these these intense electric fields in that gap requires that you build the gaps very, very small.
So there's nothing power to this. There's no power applied to this.
Well, let's be clear about it. It is being powered ultimately by the thermal energy in the device. In other words, the heat in the device is powering it. Because you're not getting energy for free here. The second law is not about that.
But there's no external power applied.
That's correct. There's
no voltages being charging the materials.
No, the charging is actually created by a trade-off. What you have here is in the N-type semiconductor you have electrons which want to diffuse out, and you have in the P-type you have holes that want to diffuse out. So when you bring these two together, these electrons and holes naturally diffuse into the other medium, but when that occurs, you get a charge separation, which creates the electric field. So it's a natural diffusive second law process, which gives rise to the second law violation, which is the irony of it all. The second law actually turns on itself here. The violation occurs because you have turned heat energy into macroscopic motion of this piston. That's where the violation comes. You have turned heat into work. That's forbidden by the most fundamental statement of the second law. If you want to define the second law in terms of what you can and cannot do with heat, then what you've done is that you have turned disorganized, random thermal motions in your solid into some rectified macroscopic motion of a block of material. You have rectified disorganized motion that violates the idea that the entropy of the universe must always increase. Here we have shown a way in which the entropy of the universe can decrease. You have taken random thermal motions and turned them into directed, coherent motions of a macroscopic block of material. So that is a statement of the second law which deals with entropy. That would have come about by Clausius in about 1865 when he first discovered entropy. A couple of years ago we hit on an alternate form of this, which actually is superior to it because you can build it more easily. This one requires very fine micro-machining of parts. A simpler version, which we're actually in the process of building prototypes for, is this, where you have the same basic idea. Again, a p-type semiconductor and n-type semiconductor arranged such that you have a positive and negative potential established between the two regions. Again, the yellow corresponds to an electric field in a gap between an n and p region. We call this the hammer. We call this the anvil. These are very thin slivers of semiconductor which are flexible. Silicon is known to be make very good springs, and these are cantilever springs. So this is a cutaway two-dimensional drawing of it. Imagine you have positive charges here and negative charges here. Under these circumstances, these positive charges would be attracted to the negative charges, and presumably this could pull down the n region, stretching these springs, causing the n region to come down, touch the p region, and short out. Once it shorts out, the electric field has been obliterated, and so there's no longer a pull downward. This material then is released. It gets pulled up by the springs. Meanwhile, the electric field can rebuild in the gap by the same thermal processes that created them originally, and then the attraction would occur again, and the hammer would be pulled down to the anvil, touch, discharge, come back. Now, we've done a number of simulations using realistic physical characteristics of silicon and p-n diodes, and we find that if you can match the time scale over which the electric field rebuilds, which we call the electrical time constant, which should be on the order of tens to hundreds of nanoseconds. If you match that time constant to the mechanical time constant of the spring, in other words, the normal resonant frequency of this cantilever, when you match these two, then you can set up what's called a resonant electromechanical oscillation, kind of like what happens when you push a kid on a swing. You hit them at the right frequency, you can build up the oscillation. Same way, you can use the electric field energy here to build up an oscillation in this hammer anvil and create a self-sustained oscillation. This can be demonstrated using today's technology. It doesn't require anything beyond which has already been developed. But again, it has to be built very small. The reasons being, the time constant for rebuilding this electric field are very short. The time constants are on the order of tens to hundreds of nanoseconds, which means that the frequencies associated with the mechanical oscillation have to be on the order of 1 to 10 megahertz, very high frequency, maybe even 100 megahertz. At those frequencies, you have to build the devices very small, otherwise they tear themselves apart by their mechanical accelerations. So they have to be built small to sustain the high accelerations and frequencies, and also to create these large energy densities associated with the electric field. So overall, this thing has to be built probably on the order of about 1 micron in size or smaller to make it work. Nonetheless, this is well within known technology. I mean, modern standard off-the-shelf transistors now are being built down to size scales on the order of about 1/10 of a micron, something like that. So using standard technology, you can build something this size.
And how do you generate electricity from it?
Well, again, if you had, let's say, a magnet here on the top of the hammer, and it were moving up and down through some sort of electric coil, it would presumably generate electrical power, like a regular electrical generator at high frequency. But this could have lots of other uses too. But nonetheless, the energy that you could get out of this, or the power you could get out of this, is actually fairly small, on the order of about 10 to the minus 9 watts on that order, 10 to the minus 8 watts, which is very, very small. It's like an ant or a flea crawling up a wall, something very small. But on the other hand, this is very small itself. So although this doesn't put out much power by itself, if you were to couple these to a large number of them, in other words, if you were to have as many of these as would fit in the volume of a desk, about a cubic meter or so, the power output for that desk instantaneously would be on the order of that of a nuclear power plant, about 10 to the 9th watts. Now, of course, that could not go on very long, because if what we're saying is true, then you're converting thermal energy, heat, into mechanical energy, and if you're creating mechanical energy at a rate of 10 to the 9th watts, that comes from heat, your object's going to cool down very fast. In fact, a block the size of a desk would cool down to absolute zero in a few seconds at that power output rate. The way you would actually use it would be to make large panels of it, very thin, maybe micron thin panels, spread them out across a wall, and then convert it and make electricity that way. So instead of having a block a meter high, you slice it into 1 million slices a meter, so now you have 1 square kilometer of this material, and then you can use it. And also, it would absorb energy a lot. It would absorb its ambient heat better. So if you had something like a chalkboard, which was paneled over with this stuff, the chalkboard here is about 1.5 meters by about 5 meters. It's about 7.5 square meters. If it's absorbing 100 watts per square meter, you could get about 750 watts of power just from that blackboard sitting there. It would cool down slightly, but it could power everything else in this room continuously forever. You'd be turning the heat in this room into work, and then using our electrical power. That electrical power would run all the computers in the room, and then the heat generated by the computer would go back into the panels, go back into electricity, and then go back into the computers again. You'd be recycling energy. The whole idea of recycling energy is foreign to our way of thinking because of the second law. We naturally assume the energy that we use coming out of the wall or used in an automobile is used once and never used again. But if you were to actually subvert the second law, and again, it has not been broken experimentally yet, but if you could reuse energy again and again forever. It would be completely recyclable energy.